Hi everyone. Today we have Sasha Gasanova that is going to speak about the periodic lozenge tiling of the plane.
Yeah, hi. Thank you for giving me an opportunity to talk. I want to say immediately that this is not really the kind of research I normally do. This talk is going to be combinatorial, not much commutative algebra. I'm going to tell you what I actually do in my next talk. This is not my usual kind of research, and this talk is based on the project which I did together with Darius Drumburg from Uppsala University in Sweden. And let's get started. So the starting point is just the infinite triangular grid, like this. Okay, this is the picture that we're gonna start with. Oh, I don't know. Like, can you read it all? Like, yeah. How do I? Oh God, I cannot move it. Well, yeah. Really? Okay. Can I move it to the side? Okay. Okay, sure. All the way to the top is good. Yeah, I suppose. Okay, anyway.
And move the pointer.
And move the what? Oh, okay. Okay, that's good. Yeah. Anyway, so the starting point is this infinite triangular grid. And well, the vertices of this grid, they form a lattice, L0, which is, isomorphic to that Z2. We're going to say that this lattice is spanned by vectors U and V, just like there. And normally you only drew parallelograms for your lattice, but I also drew these other vectors, which I call W, to make it a triangular grid, not a parallelogram grid. That's our starting point. And now I can't use the arrows anymore. Oh yeah, now I can. So now another important part of the setup is the cofinite sublattice inside this L0, inside this triangular grid. And it's given by its embedding with the help of a matrix B, which is a non-singular 2x2 matrix with integer entries. Let me show you an example. So for example, this is going to be our favorite B for the rest of the talk. And then the columns of B are gonna, span you a sublattice of this lattice. And what the columns mean, 6, 0 means you take 6 times U plus 0 times V. So everything is happening in terms of the basis that I introduced before. W is kind of, yeah. So yeah, and yeah, the second column is, 4 U's plus 2 V's. So you can see that this is really the sublattice that this matrix is going to give you. Okay. I hope you can see, right? You go 6 steps in the horizontal direction, you go 4 steps in the horizontal direction, and 2 more steps in this direction. That's how you span your sublattice. So I said the word cofinite, which means okay, these are 2 abelian groups, right? One is a subgroup of the other, and the quotient group, I want it to be finite. So point is, I want this lattice really to be 2-dimensional. I don't want my lattice to be spanned by 2 parallel vectors, right? I want really my sublattice L1, I want it to be 2-dimensional. Then the quotient space or the quotient group is going to be finite, and the size of this group is going to be exactly the determinant of the matrix, the absolute value of this determinant of the matrix. And you can see it here. You can see it here that really, in how many points do you have in L0 modulo L1? Only 12 points, right? You have like 1, 2, 3, 4, 5, 6. And then the next one is the same as the first one. And then in the second row, you have another 6. 1, 2, 3, 4, 5, 6. And then the next one is the same as this one. So modulo your sublattice, you only have 12 points, really, which is the determinant of the matrix. Okay. And if you fix a sublattice, clearly the choice of the matrix is very far from being unique. In fact, you can just swap the columns, and that's going to give you the same sublattice, but everything in this talk is going to be independent of this choice. Okay, so now there was the word lozenge in the title. It's just a figure that is obtained when you merge 2 triangles that share a common side. It's a rhombus, right, which is obtained by, merging 2 equilateral triangles, or you can say you're just removing the edge that those 2 triangles share. For example, like this. You remove this edge that goes along the vector u, you get a lozenge of type u. Clearly, there are three orientations of these rhombuses, like this. So what do we want now? We're interested in L1 periodic lozenge tilings of the planes, So there's this infinite grid, right? Which we can tile by lozenges, quite obvious. I mean, you can just take all the same lozenges, for example. You can do that. But you can do it in other ways as well. But what we want is an extra condition that this tiling is going to be L1 periodic. So whatever happens at this bold point, the same happens at this other bold point. And, you know, everything happens modulo L1. So you're looking for a tiling of the quotient space in some sense. Let me just show you an example. Maybe it will tell you much more than a definition. So this is the same pictures as before. So if I'm going to place a U-type lozenge like here, for example, then I have to place it everywhere, like modulo L1. Everything should happen modulo L1. So I should place it like everywhere next to the bold points, like on the left. Okay, I can also do this. Then I can do this, and I can do this. That's an L1 periodic tiling of the plane, right? I mean, you can see, right? It's actually even better than L1 periodic. I can even have a denser lattice. I could put bold points here, and it would still be periodic. But, you know, all I care is that it's periodic with respect to these bold points. Now, the type of a tiling is the vector that is counting how many lozenges of each type I have used. And yeah, of course, there are infinitely many, but I'm only counting them modulo L1. So then it's going to be finitely many. What is the type of this tiling? It's an easy exercise. I mean, I don't know, maybe you can see it immediately. So how many red, how many yellow, how many green? Yeah. I mean, I'm counting modulo L1, so like any region, really. You can choose any fundamental domain, right? But I mean, I shouldn't count this and this, for example, right? Hmm?
3 red, 3 yellow.
I don't see 3 red, sorry. I only see 2 red.
Yeah.
I see 2 red, I see 2 yellow, and I see 8 green. So yeah, the fundamental domain, I mean, there are many fundamental domains you can choose, and they're not really.
I guess like confusing to me is like that red diamond, like which region is it part of, right?
Does it really matter?
Because it seems to be overlapping into the next one.
Yeah, I mean, sure, but it's very difficult to choose your region so that things wouldn't overlap.
Your fundamental doesn't have to be a straight line.
Yeah, sure. Yeah, sure. It doesn't.
You don't want to overcount.
Right, but I mean, to me, it seems like there's only one red diamond that fits in the fundamental about the point. So we need to cover the fundamental, but we also need second.
What do you mean just one fits? I mean, there is 2, right? 1 and 2.
Yeah, I couldn't even see what. Okay, but the one on the top.
This one?
First, that goes above.
Well, okay, sure. You can say there is a half, but then also like you go downstairs, there will be another half somewhere below. So
you can do it via area.
You can do what?
Area. You choose a fundamental.
Yeah, if you're gonna choose some kind of a rectangular shape fundamental domain, then you will see a half of this red and another half somewhere like here, for example, right? Like this little triangle, right? So, which is exactly this thing is the upper part of this rhombus, and this is the lower part. So you can still say it's 1, but like choosing a nice fundamental domain is really difficult, like to see like exactly. So I just prefer to count modulo L1 just to say, okay, these are the same and I don't see any more, and these are the same and I don't see any more. Yeah, a nice fundamental domain is, yeah, I'm not finding nice fundamental domains. Sure, you can curve up your, or you know, you can use a fundamental domain with non-straight lines, but yeah. Yeah, but I just really I would really not think about them in terms of fundamental domains. I just want to see how many are there when you identify the bold points. I think that's a better way to see it. Okay, so I mean, as we discussed, the type is 2 to 8. I mean, there are 2 red, 2 yellow, and the rest are green. Actually, the entries of the type vector, they're always non-negative quite clearly because it's a number that counts something. They always sum up to m. I don't know how clear this is probably clear because, well, there are 12 points or m points as we discussed, right? Every point on this picture, modulo L1, it bijects onto an upward looking triangle. So if you have a point, you can biject it to an upward looking triangle by saying this point is the lower left corner of an upward looking triangle. So you do something like, you know, you're gonna say. So that way there are 12 or m upward looking triangles, and in the same way you do something like this. So point is what you call fundamental domain is going to have m of those and m of those, and each losange pairs them up. So there have to be m losanges. Yeah. You don't remember what m? M is the size of the quotient group. It's the size of this quotient group. So really how many points you see on this picture, really, modulo L1. You can also see it as the determinant of the matrix, you know. So in this case, it's only 12. You can only see really modulo L1, you only see 12 points, right? So yes, so that's the type of the above tiling. Okay, and as I said, yeah, the numbers sum up to m, they're non-negative, okay? So now the questions that I want to ask is, first of all, okay, so we fix a matrix that gives us an embedding of a sublattice, and we're interested in the following questions. So first of all, I have a vector, and you know, whose entries are non-negative integers. They sum up to m, which is the determinant of this matrix, the absolute value. Is it possible to decide where there is a tiling of this type? So for example, 2 to 8, yes, a tiling exists. I've just shown you. What about other vectors that sum up to 12 and are non-negative? Now, suppose we know that the vector is somehow admissible, that there is a type. How many other? Because like I just showed you one, there are many. Can we somehow list them? Now, the answer to the first question is yes. That's what I'm going to answer here. The answer to the second question is kind of yes, modulo subset of measure 0 in some sense. So if your type is like this, then you know you're only using one losange. So it's a boring tiling. It's just one, right? There's only one way to tile your plane using just one type. You just put it everywhere, and there is no choice. If all your entries are positive, that's another result in this paper. So we can also like classify all of them. If you have 1, 0, and 2 numbers which are positive, this we don't know, but we also don't care. Actually, this problem comes from representation theory, and representation theorists don't care what happens on the boundary somehow, so to say. So yes, so this is the theorem from our paper that classifies all the possible tilings and sorry, all the possible types of a tiling. So you have your matrix B, right? And to check whether okay, so you have your vector of gammas, right, which is non-negative, sums up to m. Actually, well, gamma 3 is kind of redundant in some sense, right? You can use gamma 1 and gamma 2, so you throw away the gamma 3. You multiply your horizontal vector gamma 1, gamma 2 with the matrix B, and you get another horizontal 2 vector, and the condition is it's an if and an if that resulting vector, the entries should be divisible by m. So that's how you check if your type is admissible, so to say. So the if part was proven by just explicitly constructing a tiling of type gamma. And that's actually one of the most exciting sentences of this talk, because, well, you have seen some pictures before, and there will be more pictures. And it's kind of cool because I took the theorem that I proved and I turned this into code. Like the pictures were coded by like, take the algorithm from the proof, make it into code. And then you modify the 3 numbers in your code and you get a totally different tiling. And you put numbers that don't make sense and it produces some nonsense. I mean, as it should be, right? So like if you put numbers that, you know, that don't satisfy the divisibility conditions. But if you put the good numbers, it gives you a good picture. And that's how some of those pictures were drawn. And I think it's quite cool to see your theorems become somehow code that produces, nice pictures. So yeah, so it's again the same example. So which types are possible here? Well, I mean, you can see, for example, I mean, I might write it here. So what do we have? I mean, we have gamma 1, gamma 2. I'm going to multiply it by 6, 0, 4, 2. That's going to give us 6 gamma 1 and 4 gamma 1 plus gamma 2 gamma 2. Those numbers have to be divisible by 12. So for example, from here we conclude, in particular, we conclude that gamma 1 is even. We can also conclude that gamma 2 is even because this number has to be divisible by 12. In particular, it's divisible by 4. This number is already divisible by 4. For this to be divisible by 4, gamma 2 has to be even. So, and then gamma 3 is also even because they sum up to 12. So like you can already restrict to gamma 1, gamma 2, gamma 3 even. So, and then you can just, go through all the possible cases and, and find all the solutions, right? So it's really, you really go through numbers that sum up to 6 and then you multiply them by 2 kind of. So it's not that many possibilities, but you have to check those divisibility conditions. And these are also all the possible types that you have. And actually types M00 and 0M0 and 00M will always be there. It's quite clear, and it's also clear that there is always, the constant tilings somehow, so that's no surprise. So these are all the possible solutions. You can just check it if you want, but yeah, I think it's not that interesting. Now I'm going to show you all the possible. I'm going to give you one example for each of those types. So these are all the types from the previous slide. So this, for example, here is 1200. This here, the yellow one is 0120. The green one is 0012. The middle one is 444. These guys on the boundary are kind of 606, 660, and 066. The guys here are of sorts 228, 822, and 282. And we have seen one of them, like we have seen this guy already, right? Like this guy is the same as our guy.
Is it always the case that a weighted average of tilings is a tiling? What it almost looks like here.
It's because the lattice is really nice, the sublattice. It's because if like if you just look at the bold points, like ignore all the lozenges, like you see how it's regular triangles again. It's just a nice lattice somehow. So yeah.
There's also like a rotation thing going on here. Like
Again,
if I take one of these things and rotate it 90 degrees, don't I get one of the other ones?
Well, again, it's because the lattice is nice. Okay, so from that divisibility condition, it easily follows that if you take all of your types and like project them nicely, because they're kind of projected on the board, right? In some sense, like point 1200, 012, 0012, you can kind of project them on this triangle. If you project them nicely, you will get the lattice you started with. So this thing is nice because the original lattice is nice. Yeah. So, and can you see it easily from here? So how was it? It's and sorry, I mean, yeah, okay. I think you could just you can just conclude it from these divisibility conditions. You just multiply everything with B inverse, something like this. Yeah, I don't quite remember, but yeah, if you nicely project your types on a nice, like for example, like this, you'll get the same. You'll get a chunk of your lattice again somehow. Okay, so now I'm going to talk about flips a little bit. So a flip is a transformation of a tiling, which is depicted below. So if you have a hexagon like this or a hexagon like this, you can just replace it with the other hexagon, right? You can just lift it, like rotate it and place it back. A vertex where you can perform this flip is called a mutable vertex. So for example, this is a mutable vertex, this is a mutable vertex. Since we want to preserve L1 periodicity when we flip, if we're going to flip at one point, we're going to flip at every point modulo L1, right? Or at all points that are equal to this point modulo L1, right? Because we want to have something, because I mean a flip is a local move, right? It changes something in just one little spot on your grid, but we don't want that. We want periodicity, so we're going to flip everywhere if we're going to flip. And then a few facts about flips. They're not so difficult facts. So if a tiling has a mutable vertex and the type is positive, well, of course, because to have this picture happening, you have to have 3 lozenges come together, or this picture. Like you see, those are 3 of different types. So there's at least 1 of each type, all right? The converse is also true. If T is a tiling of positive type, then T has at least 1 mutable vertex, and in fact, it has at least 1 of each, or 1 like this and 1 like this. That's harder to prove, but that's also true. Any flip preserves the type of a tiling. I guess there's nothing to prove there. It's very obvious, right? Okay, so then, yeah, so now, I mean, we've already answered the first question, right? Which types are, admissible? Now, somehow, now I'm getting to the second question, right? So can I have if I focus on one type, can I have all the tilings of this type? So this is our tiling, right? And I'm going to flip it. I'm going to mutate it at one of the vertices. So if you like stare at this picture a little bit, I mean, sometimes you can imagine these things as staircases, as piles of cubes somehow, right? So depending on how you squint your eyes, there are several ways to do it. Like, I mean, this thing can be either a solid cube or a corner, depending how you look at it. But in any case, to get from this picture to this picture, you just need to either place a cube or remove a cube, depending how you see it. I see it as removing a cube. So like I see this picture as a staircase where I go up, right, up, right, up, right, up, right. And here there's this staircase that I'm going to remove. And then it becomes steeper somehow. I go to up, to right, to up, to right, just because, someone vandalized my staircase and then I can't, so that's how you can see it. So that's a flip tiling, okay? And then obviously you might understand why I'm talking about flips, because maybe I can obtain all the tilings by just taking the one that my theorem produced before and just flip them in all the directions and get all the tilings like this. So I'm gonna also, so before I give the answer, I'm gonna talk about the mutation graph. So I'm gonna say, okay, I have all the possible L1 periodic tilings. There are finitely many of them. I'm going to fix the type, right? So 2 to 8 is always our type in this talk. So all the tilings of the same type, they fix a so-called mutation graph whose edges are flips. So for example, this is a mutation. This is the mutation graph for this type 2 to 8. And how much time do you have? Oh, I have a lot of time. So since we have time, we can maybe like look at this graph a little bit. So so there are vertices of type A1 up to A6, and there are vertices B and C. They're the same. I just didn't want to write stuff like B12. So, but anyway, so there are A's and there are B's and C's, right? And actually, oops, sorry. They actually correspond to these and these. So if you look at this tiling here, or actually let's look at this one first. So if you look here, this one secretly gives us 12 tilings, right? Because we can shift it back and forth, right? But instead of shifting the tiling, you should think of removing all the bold points and placing them somewhere else, right? So if I'm going to remove all the bold points, right, and place them one step to the right, like the bold point is going to be here and here and here and here and so on. It's technically a different tiling, right? So really this picture gives us 12 different tilings, right? How many mutable vertices does each of them have? Well, there is one here and one here, right? So like the mutable vertices are the tips of your staircases and the valleys, right? So this one only has 2 mutable vertices. Always compute everything modulo L1, right? Of course, it has infinitely many if you don't compute modulo L1. So So now that you draw these guys, so I'll write it here. Second picture times 12, 2 mutable vertices. Right, now what about the first picture? The same, right? I can place my bold points in other ways, but since it was more periodic somehow than the second one, it's periodic with respect to a denser thing, the first picture only gives me 6 really different tilings, because if I place my bold points here instead of here, if I shift my bold points in the direction of V minus U, so that's my V, that's my minus U, then I'll get the same tiling, literally, if I shift my bold points there, because my tiling was like more periodic with respect to a denser sublattice. So the first picture only gives me 6, really. That's times 6. It has 4 mutable vertices, right? Vertices. And well, we already saw that, for example, you can mutate from top to bottom. You can also mutate from bottom to top. So somehow, maybe this graph makes more sense now. So you see the A's are those 6 from here. And you see the degrees of every A. The degree of every A is 4, because there are 4 mutable vertices. You can mutate in 4 directions. The rest are B's and C's. They're really the same. You can call them B1 up to B12. Those are coming from here, and each of them has 2 mutable vertices. So each B and C has vertex degree 2. I think now maybe it makes more sense, right? And there are no other tilings of this type. So now comes the theorem. Another theorem from this paper that we wrote. It says if your gamma is positive, then the mutation graph is finite and connected. And in other words, any pair of L1 periodic tilings with a positive type, it can be obtained one from another by a sequence of flips, right? And then it also kind of tells you how to find them all, right? So, because for example, we know one tiling from this theorem that proves existence, right? So we know one. Now that's for example A1, right? That's the one I showed you first. Then I say, aha, I can mutate it in 4 places. I'm gonna call them something, right? I'm done with this because I already drew all the outgoing edges. Now this one has degree 2, so I have to mutate somewhere else. I can mutate back, sure, but I can mutate somewhere else. This one I can also mutate somewhere else. Oh, it turns out it's the same thing. Okay, now I'm gonna, now I'm done with these 2 vertices because the degrees are exactly as they should be. This one has 2 mutable vertices. There is no other place to mutate. This is done. Now this also needs to mutate somewhere else. So I draw here. Now this one is done. This also mutates somewhere. I draw, oh, it turns out it's the same as this. Okay, so I draw this, but now this is not done because this one has 4. This one also has 4, but we only have 2. So like you just keep drawing this graph until it closes itself, right? And it's important that this graph is connected. So you know that there is no other connected component somewhere there, right? Clearly, none of this works if your type has a 0 in it, because there are no mutations to begin with, right? You can't really mutate. So there is no mutation graphs, there is nothing.
Every vertex in your graph then have degree 2 or degree 4 or degree 2?
A's have degree 4, like you can see, like for example. Oh, they can have whatever degrees. Yeah.
But like,
Hmm?
you're tracking, right? How you
Yeah, sure. So you start with the tiling you have by the existence theorem. You look at it and you say, aha, I see 4 mutable vertices.
Oh, you're counting the number of mutable vertices in your.
Yeah. So I'm looking. So my theorem produced this one, and I'm going to call it A1. And I see there are 4 mutable vertices here, right? Like 1, 2, and 3, and 4. I'm going to be like, okay, so it has to mutate in 4 different places. I'm going to mutate in 4 different places, see what I get. One of the things is this one, and the other 3 are stuff of the same kind, just with bold points shifted. So that's how I obtain these 4. Now I see that each of those have two mutable vertices. So I mutate them further, and then, you know, you just keep going until, you know,
Okay, and then I guess you could get to the point where you do another mutation, you get 6, you could get 6 vertices.
yeah, that's
Okay.
possible. Yeah, that's
You're only
possible.
getting an even number.
This I don't know. This I'm not sure. Yeah.
Then you're getting special graphs.
Is this,
I'm not sure.
Okay, they would certainly.
Yeah, how many, like the parity of, like how many, the parity of the degree, I don't know. But yeah, but the point is, you know exactly when you're done with your graph somehow, right? Yeah. And you know there is no other connected components to this graph, so you really know when you're done. So this kind of answers the question, can we see all the tilings of a given type? And the answer is yes, if your type is positive, because you take one coming from the existence theorem, you mutate it all the possible directions. If your type is constant, meaning type M00, then you also know it's kind of boring. Type of sorts 606, I don't know, but as I said, the problem comes from representation theory, and they don't care about the boundary cases anyway, so I didn't explore this any further.
Where you can make for the vertices or the mutable vertices. And this is like, maybe if you forget the bivalent vertices, is this like a quiver, is this a cluster graph?
I thought about this, but then
A dimer model on a torus?
it is, yeah, it is a dimer model on a torus,
Okay,
yes.
It should be pretty similar to a cluster.
I think so. Yeah, if something is going on there. I know it's a dimer model on the torus, but that's all I know, so.
Semi-group with these tilings are some special kind of modules of that semi-group.
Oh, yeah, this I wouldn't know. I just did the combinatorics. I didn't quite ask myself where the combinatorics comes from, but yeah, something along those lines. But yeah, but like what makes me think about cluster stuff is the following. So yeah, so we have the mutation graph, right? But it's also possible to define a poset structure on the set of all periodic tilings of a given type. So you fix your type. It doesn't even have to be positive. You can say one tiling is bigger than the other if and only if blah. Height functions, I'm not going to talk about them, but you know, you can define a poset structure just using height functions, whatever those are. And in fact, you get a distributive lattice, whatever that is. It's a nice type of poset, okay? And then it turns out that if you define this poset that way, it turns out that the edges of the Hasse diagram, and when you draw the poset, like when you draw your lattice, right? This tiling is bigger than this, and this tiling is bigger than this. Turns out that the edges of this lattice, they're exactly mutations, because a mutation is a local move that changes your height function, whatever that is, in only one place. I'm only talking modulo L1 always. And sorry, when I say mutations, I mean non-zero mutations, right? Because like the graph I showed you before, it has cycles. It cannot be a poset, right? Because it has, I mean, this cannot be a Hasse diagram. So when I say mutations, I mean non-zero mutations. I freeze a vertex where I'm not allowed to mutate. So this was my graph, right? The dashed edges are the ones where I'm mutated at 0. I say I don't allow this. And with that, I unwrap my thing, and that becomes a lattice, which I can prove it is a distributive lattice with edges that are non-zero mutations, well, edges of the Hasse diagram. So all of this mutation, frozen vertices, all of this reminds me of some cluster stuff, but yeah, I'm not sure. Yeah.
Sort of like a secondary point situation. This sort of has a view of what's kind of that.
Secondary point. Well, what is a secondary point?
For a polytope, for instance, you look at the set of all triangulations.
Oh, I see.
And this is
periodic
thing.
Right.
Kind of that. And then you have a edge between them. You have a bicell flip, which is very similar.
Which is similar to what's happening here, right? Oh, I don't know. And can I ask you more about this after the talk? Yeah, I don't know. But yeah, that sounds, yeah. Yeah, so how much time do we have? Oh, that's still a lot of time. So now I'm gonna give you a few final remarks about this. So first of all, the results from here, they can be generalized to arbitrary dimensions. It's just your matrices are bigger, your vectors are longer, but the divisibility conditions are the same, the mutations are the same, height functions are defined similarly, and so it all works in higher dimensions, but good luck figuring this out without first figuring out the two-dimensional case, right? So we really had to complete the first project first, and then to say, actually, if you don't use the intuition, if you just use the formulas are just the same, they're just longer, but yeah. So all of this happens in arbitrary dimensions. And 2 is the second paper that I wrote with my co-author. Now, yeah, this problem is clearly very combinatorial and it's interesting on its own, but it stems from representation theory. If you look into our paper, there are like scary words like pre-projective algebras, Mackay quivers, something, Calabi-Yau, something, I don't quite know. Yeah, so the thing is, yeah, I don't quite know what my co-author wanted from these tilings. What I know, I know exactly what he did not want, though. He did not want to do combinatorics. And then I was like, hello. He just knocked on my door and was like, I cannot count, help. And I was like, you can count on me. So that's how I ended up in the project, yeah. I have no idea what's going on in the representation theory part. I mean, I have some idea, but it's yeah. I mean, to finish this as soon as possible, I just had to do my part like as quickly as possible. So I didn't quite get into the representation theory part. So maybe someone here can teach me about it. So what else? Yeah. So the combinatorial part was inspired by a preprint that we found on Archive. There was a preprint that we found that literally that is literally titled "Periodic Lozenge Tilings of the Plane," but the preprint was never published. The persons seemed to have left academia. The statements were not so easy to understand. Like the language of the statements was a little bit difficult. The proofs were incomplete, so we didn't feel the courage to just cite the preprint. So what I learned from that paper was I translated into easier language what it is that I want to prove, and I learned some techniques, but I wrote all the proofs from scratch because I mean the proofs were quite incomplete and never got published. So as I said, the person seems to have left academia, and we had moments like me and co-author like trying to read that paper and being like, this corollary they claim follows from theorem 5, and I would be like, do you understand why this just follows from theorem 5? And my co-author would be like, yeah, I don't think even theorem 5 follows from theorem 5. So yeah, I mean, stuff like this. So we were like, okay, we understand the techniques, we learned the height functions from them, we understood what we had to prove, kind of, we translated it into easier readable language, and then we did everything from scratch. So but we still of course gave them credit because, you know, without them, we wouldn't have done it. And these are the references that I mentioned, and thank you.